Assalamu alaikum guys, welcome. Okay, so now in this video we are going to talk about a very important topic of intermolecular forces, hydrogen bonds. Okay, so what are hydrogen bonds? The very first thing is its definition, which has been asked for like 2 to 3 marks many times on the past exams. So now let's see. It is a type of intermolecular forces, the strongest intermolecular forces, which is formed or which exists between an electron deficient hydrogen and a more electronegative element. By electron deficient hydrogen, we mean that the hydrogen which is directly bonded to any of these three atoms, or I should say a hydrogen which already has a very strong partial positive charge. Hydrogen bond is actually a special type of permanent dipole interaction. Remember permanent dipole interaction from the previous lecture? Permanent dipole interaction was the interaction that existed between permanent dipoles, right? Dipoles are basically the molecules that contain elements of different electronegativities bonded to one another, which have a large difference in electronegativity, resulting in a partial negative charge on the more electronegative element and a partial positive charge on the less electronegative element. Now, hydrogen bonds is a special type of permanent dipole interaction, but the only difference is that the difference in between the electronegativities is very huge. Okay, so if you are asked to define hydrogen bonds, so this is the definition till here. Okay, for 3 marks or 2 marks, you must mention these 3 elements: nitrogen, oxygen and fluorine. Reason: because fluorine is the most electronegative element of the periodic table, followed by oxygen, and then nitrogen is followed by oxygen, right? So these are the 3 most electronegative elements of the periodic table, and they are very important for the formation of hydrogen bonds. Both the hydrogen atoms must be bonded to them, and the hydrogen atom must form a hydrogen bond to them. Okay, so both of the conditions must be fulfilled. I'm going to explain on this over here in just a bit. So let's get towards this. Okay, so now I need your undivided attention. How does the hydrogen bond form? Okay, I'll come here. Now, the very first example is, let's take the example of oxygen. When hydrogen atom is directly bonded to oxygen, it becomes electron deficient. Okay, this is what we mean by electron deficient, because hydrogen itself has a very low electronegativity, right? From your previous lectures, you might remember that. And oxygen is very electronegative, as we have it in this list over here. So the oxygen is more electronegative than the hydrogen. It will pull the electron density, the bonded electrons, towards itself, and will get a partial negative charge. Of course, the electrons won't be fully transferred, otherwise it would become an ionic bond, but rather the electrons would just slightly be shifted towards the oxygen atom, right? The shifting of electrons would induce the partial negative charge on the oxygen atom, whereas it will induce a partial positive charge on the hydrogen atom, and this hydrogen atom, which is directly bonded to either an oxygen or a fluorine or a nitrogen, is an electron deficient hydrogen. Clear? Now you don't need to make these 2 electrons over here, so we'll remove it. Now, if you are asked to, okay, let me first explain it, then I'm gonna tell you the stuff that you need to have in your exams. Now, same will be the case with another water molecule over here. The hydrogen atom will be electron deficient. The oxygen atom is gonna be more electronegative, so we'll get a partial negative charge. Now, a hydrogen bond will form between the partial negative and the partial positive poles of water. Where are you going to start it out from? You are going to start it out from the lone pair of oxygen. Okay, from the lone pair of oxygen, the bond must form and it must terminate on this hydrogen atom over here. This is the first hydrogen bond which has been made. The second hydrogen bond can be made from the lone pair, the second lone pair of oxygen, to this hydrogen over here. These are the 2 hydrogen bonds which are made. You have to show them by a dotted bond. Okay, you are not supposed to show them by a solid bond, because hydrogen bond is not an actual bond, it's just a dotted bond. It's a force of attraction. Okay, so this is how the hydrogen bonds are made between 2 water molecules. Now, even if you didn't have a water molecule over here, rather you had a HF molecule over here or an ammonia molecule over here, even then you would have gotten a hydrogen bond being made. Okay, then, and similarly, if you had another water molecule over here, it would have formed a hydrogen bond with this hydrogen over here or with that hydrogen over there. Okay, now coming to HF. HF, the fluorine, is the most electronegative element of the periodic table, and the hydrogen is bonded directly to the fluorine, right? Now you can get an hydrogen bond between the partial positive hydrogen and the partial negative fluorine. Okay, and that's the hydrogen bond that you have made. Remember, the hydrogen bond must be between the negative and the positive, okay, not between the negative negative or the positive positive, and it must start out from the lone pair and must end on the less electronegative element, that is the hydrogen itself. That's why it's called the hydrogen bond. Now coming to ammonia. In case of ammonia, nitrogen is the more electronegative element and hydrogen again are going to become the electron deficient elements. And then you can start out from the nitrogen and end it on the hydrogen again by a dotted bond, and that's it. And you must show the partial charges. Now what does the examiner mark you for in these diagrams? The first mark is for all these partial charges to be made correctly. Second mark is for starting out the bond from the lone pairs. The third mark is for making them dotted, and the fourth mark is for ending them correctly on hydrogen and not on some other element. Okay, so this is how you're gonna make the hydrogen bonds. Similarly, if you have bigger molecules containing H and F directly bonded, or H and O directly bonded, like carboxylic acids or alcohols, of course, then you can make hydrogen bonds over there as well. Now, coming to the very common question on the exams is that the examiner asks you to compare or to explain why does the melting point or the boiling point of water differ from H2S, hydrogen sulfide gas. Hydrogen sulfide gas, by the way, is a gas. If you get it in the laboratory, it is gonna have a rotten egg smell or a bad egg smell. Okay, that's a characteristic of hydrogen sulfide, H2S. Now, water versus H2S. Why is there a very huge difference in between the melting and boiling points of water and H2S? That's the question. So basically, water, as you guys have seen, has the hydrogen bonds. H2S, hydrogen sulfide, on the other hand, doesn't have hydrogen bonds, although their structures are similar. Okay, H2S, the only difference is that it has the sulfur and that water has an oxygen, but there is a huge difference between the melting points. Water is a liquid, H2S is a gas. That's the biggest difference, right? Water has a higher boiling point, meaning 100 degrees Celsius, as compared to H2S, which has a boiling point less than the room temperature. That's why it's a gas at room temperature, right? So now the difference is, so what are the answers, the points that you must include in your answer while answering this type of question is, the first of all, you have to mention the intermolecular forces. Secondly, you have, if the states are not given, you have to mention the states. Okay, and that's generally for 2 marks, or it's an MCQ sometimes. So water has stronger intermolecular forces, that is, it has the hydrogen bonds, and hydrogen bonds are the strongest intermolecular forces out there. H2S, on the other hand, has van der Waals forces, right? So van der Waals forces are weaker than water. Van der Waals forces, that's why it's a gas. So if they are weaker than hydrogen bonds, so therefore water is a liquid, meaning has a higher boiling point than H2S, because more energy is needed to overcome the hydrogen bonds as compared to the van der Waals forces, and that's it. Okay, now the second question comes to compare and contrast HF with HCl. HF, which we've drawn over here, the melting point or boiling point of HF as compared to HCl. HCl, hydrogen chloride, can be a gas at room temperature, by the way, and HF is a liquid. So now why is this the big difference? So basically, water, HCl, has been discussed as a classical example in the previous lecture for permanent dipole interaction. Remember, HCl has permanent dipole interaction. As I told you, hydrogen is bonded to the chlorine, partial negative and partial positive, but this difference in electronegativity is not very huge or not very large for the bond to be made between the two HCl molecules to be stronger, to be considered stronger. So the bond which is made between the chlorine and the hydrogen over here, this is very weak. This is permanent dipole interaction. This is weaker than the hydrogen bond which is made between HF and HCl. So what are the points that you must include in your answer? First point, HF has hydrogen bonds. Second point, HCl has permanent dipole interactions. You've identified the intermolecular forces, then you have to mention that hydrogen bonds are the strongest intermolecular forces, therefore more energy is needed to overcome them, therefore HF has a greater melting and boiling point as compared to HCl. Simple. Then the third question, that is a very favorite examiner question, is that they give you all the 4 halogenic acids HF, HCl, HBr, HI, and they asked you to compare and contrast the melting and boiling points of all of these. Right now, for this, what you'll actually need to do is you'll have to, and sometimes what they actually do is they give you a graph basically, which starts out from HF, then HCl will have a lower melting point, then HBr will have even lower melting point, but HI has a greater melting point as compared to HBr. Can you guys explain this graph, by the way? Okay, so in order to explain this graph, what we actually need to do is we need to again mention the intermolecular forces first. HF has the highest melting point because it has hydrogen bonds. HCl has permanent dipole interaction. HBr and HI, since they are very less polar, so they'll most probably have the van der Waals forces as a dominating forces because they are less polar, or they are the least polar in this series, right? Now, as we go from HBr to HI, what happens? There's a change. Since both of them have van der Waals forces, HI has a higher MR, a greater number of polarizable electrons, therefore it will have a stronger van der Waals forces. HI will have stronger van der Waals forces as compared to HBr, therefore more energy will be needed to overcome them, and therefore HI will have a stronger or a greater melting point as compared to HBr. Okay, this is a classical example question that has been asked on the past papers, like tons of times. So HI, why is HI above HBr in melting and boiling point? Because HI has stronger van der Waals forces, and if you are asked to explain why is that so, you have to write down the three conventional points which I have mentioned in the previous lecture on van der Waals forces. What were those points? First of all, greater MR, secondly, greater polarizable electrons, third, stronger van der Waals forces, and more energy needed to overcome them. If you have to compare HF and HCl, I've compared them already, that HF has hydrogen bonds and HCl has permanent dipole interaction. So HF, since it has hydrogen bonds, so it's gonna and hydrogen bonds are the strongest intermolecular forces, therefore HF will have the greatest melting point. HCl has permanent dipole interaction, HBr and HI have van der Waals forces, so and HI has a greater MR and more number of polarizable electrons and stronger van der Waals forces as compared to HBr, therefore it will have greater melting point as compared to HBr. Okay, so this pretty much sums up, compares all the three types of intermolecular forces in a single graph over here, and this is actually a favorite examiner question. He actually wants to test you guys on all the three types of intermolecular forces collectively in the same question. Okay, meaning the first part might be on van der Waals forces, the second part might be on permanent dipole, third part might be on all the three comparison between all three and stuff like that. Okay, now the last and final section of this video, water has several peculiar characteristics. Okay, several peculiar abnormal characteristics. So why is that so? Well, those abnormal characteristics, whenever you are given an abnormal characteristic of water and you are asked the reason, guys, remember 90% of the time the answer is due to the hydrogen bonds. Okay, one peculiar characteristic is that ice, although is a solid state of water, it is less dense than water liquid itself. Why is that so? That's because of hydrogen bonds. When the water molecules, they join together in forming ice, the hydrogen bonds, they cause the water molecules to separate out from one another and increase the volume in between them. Okay, I'm not drawing out the structure of ice. You can search it out on Google. But the water molecules, they are going to be separated from one another. And if the water molecules are separated from one another, large vacuums or large space, vacuums, we can't call it vacuums, but large spaces are formed. Volume increases, therefore, and density is mass per unit volume. If the volume increases, the density has to fall down. So it's actually due to the hydrogen bonds that ice floats on water. Then second is that the latent heat of vaporization, latent heat of vaporization and latent heat of fusion, both are higher for water. Reason is again hydrogen bonds. If adhesion and cohesion, adhesion means sticking to a different molecule and cohesion means sticking to one another. Okay, so for instance, water molecules over here, if you have water, the water molecules tend to stick to one another. Why is that so? Because of cohesion, and the cohesion is due to the hydrogen bonds in between them. They stick to one another due to the strong hydrogen bonds. And adhesion means sticking to a non-water surface. Water molecules sticking to a different surface. For example, if you capillary reaction is due to the hydrogen bonds of water. Capillary reaction means sticking to the walls of that capillary tube, right? It's due to the hydrogen bonds. Water can form hydrogen bonds with the walls of the container. Or why does water stick to the container? Okay, why does it cause wetting? Wetting is due to the hydrogen bonds, because water can cling to the surfaces. Okay, and that's due to the, because it can form hydrogen bonds with the surfaces. And then why is the boiling point higher than expected? H2S compared to water, we've explained that. That's because of the stronger hydrogen bonds. And then lastly, pond skater. Pond skater is an insect that slides on the ponds, on the waters. Why can the pond skater walk on the surface of water, on the surface of ponds? And the reason for that is because it can walk on the hydrogen bonds in between the different water molecules which are formed in that particular pond. And yep, this sums up everything about hydrogen bonds, and this actually completes our discussion on intermolecular forces. So if you are asked any question after this video to compare and contrast between different molecules of different nature, like polar versus non-polar, HCl versus HF, HCl versus ammonia, or stuff like that, I hope you guys can explain that now with all of this information given to you. And guys, this lecture is very, very important. Do make notes of it and do learn it very nicely. Okay, thank you.